Sounds good. Yeah. Thank you for the introduction. Yeah, it was spring of 24, I believe I gave a talk at Georgia Tech. So yeah, excited to be, thank you for the invite to give another talk. So excited to talk about some of my research. So as Huria mentioned, I'm currently a postdoc at Johns Hopkins in the Haptics and Medical Robotics Laboratory, where I largely do a lot of research exploring human perception. So today I'll be talking a bit about that. A quick bit about me. I'm originally from a city called Rancho Cucamonga, California. It's in Southern California, about an hour northeast of Los Angeles. And from there, I went and did my undergraduate education at Yale in mechanical engineering, my graduate education at MIT in mechanical engineering, and now postdoc in mechanical engineering. And as Maria mentioned, I'll be an incoming faculty starting in August of 2027 at Georgia Tech, also in mechanical engineering. Um, and I am not looking for PhD students this cycle, but I will be next cycle. So if any of the research that I mentioned is of interest to you or any of your friends, feel free to connect with me on LinkedIn. I'll actively be recruiting in about a year or so. So going into, or actually, let me highlight at the bottom. I will be talking. You can follow this timeline to kind of understand where we are in the talk. I'll give a brief background of my research approach. I believe there's two papers of mine circulated, one of which involved cross-modal matching, which we'll be talking about that, and one of which involved the visual perception of dynamics. We'll be talking about that. But going into my research, I'm really largely motivated by this performance gap between humans and robots. So as you can see in your screen, humans are very capable of doing just a plethora of complex manipulation tasks. And these robots at the Toyota Research Institute, while and growing increasingly capable due to aspects of behavior cloning and reinforcement learning, and different aspects of reinforcement learning, are becoming increasingly capable. They're still not achieving the activities that us humans are capable of doing. And we call this performance gap the paradox of human performance because when you look at people's wetware, they appear to be doing more with less. In fact, our wetware and our hardware is worse than robots. We have actuators that are an order of magnitude slower, communication that's 6 orders of magnitude slower, and feedback delays that are 2 orders of magnitude greater. So even with inferior hardware, we can outperform robots. And the key question becomes how? And that's kind of where my goal of my research comes in. I want to develop simple models and use control theory to better understand human motor control, perception, and learning. And I like to draw upon this picture that kind of describes my research paradigm, and I'll go a little bit into detail about that. But I believe my research paradigm can help bridge the gap between robots and humans. And from understanding, using simple models to understand human motor control, perception, and learning, we also have applications in robotics, rehabilitation, and skill acquisition. If we can use control theory to understand how humans produce movement, or if we want to understand how humans perceive movement from a mathematical standpoint, this can allow us to better rehabilitate people who have lost movement, and can also allow us to better teach skills or complex skills of people who want to gain these new complex skills. So talking a bit about my research approach, my research is very heavily involves human subject experiments where I'll collect experimental data and try and tease back information about what control inputs humans are using to produce their movement. And that paradigm will involve trying to model the task in the human using simple models and then using control theory to sort of peel back at those layers of what is the control input that is leading to the experimental data that we're observing. I want to highlight that during my PhD at MIT, that's where I gained a lot of expertise in using this motor control theory to try and understand behavioral subject information. And we looked a lot at what we call this forward path of some aspect of this input and then an output of behavioral information, trying to model this forward path. However, as I will talk about today, something that's very important is this feedback path, which I call perception, where now you're using different sensory inputs to also inform your motor controller, to also inform your control theory about how humans are producing movement. And I'm getting the expertise in this during my postdoc in the Haptics and Medical Robotics Laboratory, and that'll be the focus of the talk today. And then I guess I should highlight this whole research paradigm is what I plan on bringing to Georgia Tech in the summer of 27. So just giving a brief overview of some of my prior work, so my PhD work looked largely at complex manipulation tasks, where we looked at these ideas of synergies and tried to understand different aspects of some simplifying controllers of how humans produce movement and complex manipulation tasks. And I don't have time to talk about that today, but if you are curious, you can scan this QR code and see some of the work of my PhD defense, which is in the talk that Hiria mentioned previously. And I also like to just show this. It's fairly cool. One aspect of human subject research we did involved looking at piano playing, which is kind of cool because for a week we had some very expert pianists come in and play pieces in our lab, and it felt like we were a bit in a concert for a couple of weeks. I don't think is the sound playing on your guys' end?
No, I don't hear anything.
We can't hear anything.
Okay, that's unfortunate. It was beautiful, but we'll move on. Not enough time to figure that out at the moment. But you have to take my word for it. So, like I motivated previously, most of my prior research was in that sort of forward path, trying to understand how humans produce movement. And one key question that sort of lacks is, what about haptic feedback? What about that tactile force feedback and that provides information for when you're doing these complex manipulation tasks? And as I said, I'm currently in a haptics lab, so I'd be remiss if I didn't show you this classic canonical video of the importance of haptic feedback, where here you see a person who is picking up a match and lighting a fire with the match very easily. And then in this next procedure, what we will show is that a clinician will go and basically numb the finger such that you don't have force feedback at the finger. And you don't have tactile feedback at the finger, so you don't get that sort of sensation. And then they'll ask the participant to do the exact same task of trying to light a match. And what you'll see is that the participant is now struggling to even pick up the match, struggling to light the match. So because they're trying to do this fine-grained dexterous task without tactile feedback or force feedback, they are starting to struggle, which sort of highlights the importance of haptic feedback, especially in complex manipulation tasks. One thing that's really striking to me is that I believe complex dexterous manipulation requires both haptic and visual feedback. And I think this video is a very good example. You know, if we think about the difference between human and robot performance, this is a great canonical task when you're seeing not only is it kind of cool that this person's juggling and simultaneously solving a Rubik's Cube, but also you can see that they're doing things that are very complicated for a robot to do, trying to do trajectory planning of throwing an object and catching an object, coming in and out of contact. And then from a motor control standpoint, one thing's really interesting is when you see them slow down, you can see that the participant or this person is focusing on the object in the air and only using their hands, the tactile feedback in their hands to manipulate the Rubik's Cube. So they're really heavily relying on both haptic and visual information. And from a research standpoint and a rehabilitation standpoint, researchers leverage multimodal feedback or multisensory rehabilitation as well. So shown in these videos, you see a participant or a stroke survivor who trying to lift up or trying to do a peg and hold task with their unaffected hand. Here, they're trying to do the same peg and hold task with their affected hand. After stroke, it's known that we have these motor deficits. And in rehabilitation paradigms, to try and rehabilitate people's ability to do these activities of daily living or these simple manipulation tasks, we try and give them different aspects of feedback. And that could be visual feedback, tactile feedback, kinesthetic feedback, or auditory feedback. However, it's been shown that most people often try and incorporate multimodal feedback, giving them different aspects of sensory inputs to allow them to do this task. And in fact, we have a device in our lab called the hand device, which actually is designed for multimodal rehabilitation, where at this interface, it gives vibrotactile feedback, while also and a graphical user interface that you'll see later on gives visual feedback in trying to rehabilitate people's ability to do a pinch grasp for fine-grained movements, rehabilitate stroke patients specifically. However, with multimodal feedback, there's this challenge that people have highly individualized deficits, and there's variability in the rehabilitation setups, and this leads to a lack of perceptual equity, which is the equivalence of sensory inputs. And this is important because you can imagine if I'm giving you two sensory inputs, and one of which is very salient, very rich in information, and the other of which is not up to par, you might go and just completely ignore the sensory input that doesn't provide a lot of information. So there's this mismatch in sensory inputs. If you have one that's very useful and one not so useful, you might just ignore it, and that makes the paradigm or the research effectively be unimodal, right? You're not having multiple inputs because people are ignoring one as noise because it doesn't have as rich of information. So the goal of perceptual equity is to sort of bring these two sensory inputs back together. And that's the problem that I just mentioned. Perceptual inequity confounds research results because you're expecting people to use two feedback or two sensory inputs to improve their function or do a particular experiment, but they're ignoring one because they're just tuning into the one that provides the most amount of information. So the question becomes, how can we provide perceptual equity if perceptual inequity is a bad thing? And our solution is cross-modal matching. So we saw this, a master's student named Anway Pimpelkar and I in the lab came across this idea of cross-modal matching and believed that it could help us with this problem of perceptual equity that we were running into with other experiments. And namely, cross-modal matching, just to give it just to give a definition, it can establish perceptual equity, which is the equivalence of two sensory inputs across sensory channels prior to multimodal rehabilitation, helping account for variability across individuals and setups. An emphasis on this prior to multimodal motor rehabilitation, because ultimately it is sort of a calibration step. This is prior to your rehabilitation, prior to your experiment. You want to equate these sensory inputs. So what is cross-modal matching? It's done in two phases. The first of which is exploration phase, where let's say you have two sensory modalities, one of which we'll call visual, which is just the brightness of the sphere, and the other of which we'll call haptic, which is a vibration, the amplitude of a vibration you feel. During the exploration phase, what you'll do is you'll be given the ability to explore the full range of these two stimuli, and you're asked to explore the full range and find the equivalent between the two. So you have a range, and you're asked to understand what is 50% of visual stimulus, what is 50% of haptic stimulus, and understand that the 50% are, understand what's 50% in one domain and what's 50% in the other domain. Same with what's 25% in one domain, what's 25% in the other domain. We're trying to have you understand this relationship, this prescribed relationship in this exploration phase. And then the second phase is the matching phase, where we've asked you to learn this prescribed relationship, but because people are variable in how they perceive things, what people learn will be variable. So what we'll do is in one domain, we'll give them a constant reference stimulus. So we'll say the sphere is this bright. Bring that to the same level of haptic intensity that you learned previously. So let's say you perceived it to be 33% of brightness. Now we want you to bring this haptic intensity to 33%. And then you'll do that again in the opposite direction, where you have a haptic reference and a visual matching. And this is a very simple paradigm, but very few people in motor rehabilitation use it. And the reason is because really it is a calibration step, and it can cause patient fatigue, right? Creating this matching paradigm requires a lot of trials. It can be leads to long protocols, upwards of an hour, which is very impractical for clinical applications because it's really just like sort of a daunting step. And this is prior to actually even getting to the rehabilitation or to the experiment. So the goal of our work is to optimize cross-modal matching and then also to motivate perceptual equity and multimodal motor rehabilitation. So just to briefly recap, we ask participants in cross-modal matching, we ask participants to perceive and learn a prescribed linear relationship. However, because humans have perceptual differences in the way they perceive stimuli, they will likely learn different mappings. And capturing these different mappings and prescribing them into multimodal research studies is a way to enable participant-specific perceptual equity. And we believe this step is crucial in multimodal rehabilitation and experimentation. And this brings us to the paper that I think was circulated prior to this, where the main goal was to optimize cross-modal matching. So how exactly did we do that? And the first phase we did, the first phase was exploration, where the goal was for people to learn the relationship between the haptic and visual stimulus. Using the hand device, we gave a haptic stimulus, which was just vibration at the index and thumb fingers. And then we had an illuminated sphere where the brightness of the sphere changed as the visual the visual stimulus. So you can see in the exploration phase, there was this GUI where they could learn this range of haptic intensity using the vibration. They could switch to the visual intensity, which changes the brightness of the sphere. And the goal was to learn the mapping and the equivalence of the two. So if we're at 50% haptic intensity, what is the equivalent of visual, and so forth. Then we move to the matching phase, where the goal is to obtain an individualized mapping for subject's perceptual baseline. And the way to do this is basically we have a reference stimulus. In one case, that might be visual or it might be haptic, but we have 8 evenly spaced intensities repeated 4 times in a block randomized order, which means we give them a constant, for example, visual stiffness, and then we ask them to adjust the haptic stimulus that they feel. They do this 32 times in each direction. And then this full data set could be quite long, right? If we give people 60 seconds per trial to do the matching, and we're asking them to do 64 trials, that gives us 64 minutes. So again, this calibration step is over an hour long. So the question becomes, how can we best model the mapping from one intensity to, if the goal is to optimize cross-modal matching, there's 2 steps. The first step is to answer, how can we best model the mapping from one intensity to the other? So just to test this, we tested 2 fits, the first of which is a linear fit, where we have the reference stimulus and we have the matching stimulus, and we just fit a linear line to it. The second, we fit an exponential line. And then we also tested 2 data preprocessing types, where the first of which is no preprocessing, which we just keep all the data. We refer to this as all data. And then the second of which is we average the match intensity across the common reference intensity, which means we just average the data points. And then we also add a data point at the origin. And this was done because we sort of assume that people are able to understand what 0 is. If we give them 0 vibration, they should be able to perceive that this is 0, and they would match the 0 visual stimulus as well. They can understand nothing is nothing. And then from these mappings, what we can do is we can use the coefficient of determination to determine the most descriptive mapping. Which of these mappings describes the data that we've collected best. So to kind of internalize this, what we see from one specific subject might be we have their reference intensity, in this case the visual, and we have the 8 different intensities that we've given them, and they've been shown 4 times. So for each of these, you should see about 4 blocks. And this is the all data case. And then the average plus origin case, we've just averaged across reference intensity. And then we've also added, so we've averaged across reference intensity to get 1 data point at each intensity. And then we've also added this data point at the origin. And then we fit both a linear line in the light blue and then an exponential in the dark blue. And then what we can do is populate all the subject data and look at the R squared, or the coefficient of determination, and start to ask which mapping performed better, the linear, the exponential, the all data, the average plus origin. And after running a 2-way ANOVA, we find that the linear fits outperform the exponential models overall. So the light blue outperforms the exponential. And this makes sense, right? And it aligns with the inherent linear nature of the task. We prescribed a linear relationship, so we should expect that people will get a linear mapping. So this is a nice intuitive result. We like those because it kind of confirms that what we're doing is correct. And then second, we found that the average plus origin yielded the highest R squared values. So from these 2 key results, moving forward, we have a mapping. Now the next step is to try and reduce this mapping. Basically, this previous experiment, we got this mapping, but it took 64 minutes. The goal is, how can we get this same mapping in a shortened, optimized manner? So to answer this question, what we did was we ran a Monte Carlo simulation for each participant, such that we basically took their data and eliminated some intensities and some blocks. And we gave the option of having any combination of 3 to 8 intensities and any combination of 2, 3, or 4 blocks, which gave 657 conditions, and found out which combinations minimize this cost function. which aims to minimize the amount of time it takes, and the error from the mapping of the full data set. So what's shown here is the original average plus origin data set with the full map. And basically what we want to do is ask what data points can we eliminate to still get the same. And what we found is that to get a similar mapping, we just need 3 to 5 intensities and 2 to 3 blocks. And namely, specifically found that it's important to have a reference intensity at 2/9, 4/9, 8/9 in our particular case. And this is exciting because it reduces the time that this task takes. We reduce it by 5 times as much, and this calibration task now takes 5 to 18 minutes, which is much more feasible. So just to recap, what we found was that the average plus origin data set with the linear fit produced the best fits, and this is intuitive as it matched task structure. And furthermore, we optimized the protocol by reducing the time 5 times, which now creates a nice, quick and low fatigue calibration for our multimodal experiments and rehabilitation paradigms. So I just want to highlight that cross-modal matching is important. We want to take these 2 sensory inputs and bring them to a level of equivalence such that they provide the same amount of information such that a participant is able to use both of them equally. And because we've optimized this task, cross-modal matching can and should be implemented before any multimodal motor experiment or rehabilitation paradigm. Also want to highlight Anwe and I put together this phone app called Sense Match to enable cross-modal matching on a smartphone. In our previous experiment, we had this hand device, which gave a graphical interface of brightness on a phone and also vibrated, or brightness on a screen, and then also vibrated. Well, a cell phone can do both of those 2 things. So now we can implement this research paradigm on a more ubiquitous platform and make this possibly rehabilitation paradigm more ubiquitous and able for participants to use at home. And we recently published this paper at the Conference of Neuroengineering. So if you're going to be there, feel free to talk to me about this paper if you're curious. So now that we've created this cross-modal matching paradigm, we've optimized it, we've said that it should be implemented in any multimodal experiments. The next question is trying to ask, does it work? If we actually do the cross-modal matching and bring these 2 perceptual inputs to equivalence, does that lead to some testable hypotheses? And specifically, we want to test the hypothesis that perceptually equivalent sensory inputs with perceptually equivalent sensory inputs, participants should be able to, 1, use both percepts equally to perform a task. So if we ask them to do a task with 1 sensory input, and then we ask them with only 1, and then we ask them to do it with only the other one, their performance should be the same. And then on the other hand, they should be able to integrate both of these percepts to achieve better performance with both than when they had with just 1. So to test these hypotheses, what we conducted was what we call this pinch task, where we use the exact same sort of graphical user interface, but now we want to highlight this hand device, and in addition to giving vibrotactile feedback, it also has these 3 degree of freedom force sensors. So now you can isometrically apply forces on this device and measure them, and the measured forces will be used in this graphical user interface to move these smaller spheres to come in contact with this virtual sphere. And the goal of this experiment is we wanted participants to learn to hold the ball in a specific force range for a specific amount of time. And if they applied too much force, they would break the ball. If they applied too little force, they would drop the ball. So the goal is to hold the ball with the right amount of force. And then similarly, we gave them the same feedback paradigm, where if they have the visual feedback that illuminated the sphere, and then they have the haptic feedback that vibrated. And to give more details about the experimental task, there was about 5 experimental blocks, but there was an initial block 0 where we had 12 training trials, where during the training trials, they were given both visual feedback and haptic feedback, and some coaching on how to apply pressure. So decrease pressure, maintain pressure, increase pressure. And they're supposed to learn during this task both the visual feedback that provides the correct force that they're supposed to apply, and then also the haptic feedback that provides the correct force that they're supposed to apply. So after the training trials, then we moved to one baseline block where we had 12 trials with no feedback, where there was the spear did not illuminate and the hand device did not vibrate. And then we had blocks 2 through 4, which were the 3 experimental trials where we had 24. There were the 3 experimental blocks where we had 24 trials of either solely visual feedback, where the spear illuminated, solely haptic feedback, where the hand device vibrated, or visual and haptic feedback, where you got both the spear illuminating and the hand device vibrating. And then we finished with 12 no feedback trials to kind of get a washout effect to see if subjects learned or participants learned or not. And in this experiment, our key dependent variable was success rate. So how many trials were they successful in maintaining the right amount of force on the virtual spear? And the key hypothesis that we wanted to test was, I guess, if we actually did our cross-modal matching correctly, then the visual success should equal the haptic success, and the success of the combined visual and haptic block should be better than the individual visual block and the individual haptic. So what were the results? We see here is the success rate of participants as a function of feedback condition, where we had no feedback, and we had the visual only, the haptic only, and then the visual plus haptic. And we can ignore these black bars. All they're really saying is that these feedback conditions are performing better than the no feedback conditions. So what's important is these colored significance bars, which show that the visual feedback was better than haptic feedback. This, which is, again, counter to our hypothesis. If we actually did the cross-modal matching correctly and we brought the visual feedback to the haptic feedback in equivalent manner, then these 2 bars should be, and that was not the case. And then similarly, our other hypothesis was that the visual and haptic feedback should be significantly better than both the visual and haptic. And it was better than the haptic case, but it was not better than the visual case. So just to recap, despite bringing each sensory modality to equity, participants did not perform the same using visual and haptic feedback. Moreover, participants did not perform better with 2 sensory inputs as opposed to 1. So now we're all sort of perplexed. We're wondering what the heck is going on. And we kind of preached the last 20 minutes about perceptual equity and bringing these tasks to equivalence. And we found out that, doing this doesn't matter. And I think the reason is that for simple tasks, humans are visually dominant. So our North Star was kind of this idea of you have to do this very complex manipulation task where you're coming in and out of contact. You can only look at some objects. You have to rely on haptic information. And only when you're forced to rely on haptic information do you use it as opposed to using visual information. So we haven't completely given up on cross-modal matching. What we want to do in the future is trying to do this with 2 haptic domains and completely get rid of the visual domain, where we have this new hand device where we have these pneumatactors on the fingers that inflate, and they provide pressure feedback of the finger. And currently have a master student in the lab, namely Bert Kosmikan, who's working on that alongside me. And then other future work is given this hypothesis that humans and even stroke survivors are visually dominant, we believe cross-modal matching can be used as a simple experimental paradigm to assess sensory deficits using that phone device we talked about called SenseMatch, where if we believe that people are visually dominant and maybe their vision is not impaired, then when we have them do this cross-modal matching task and they don't learn this linear relationship, the errors in which the deviation from normality of how they learn is purely a function of these sensory deficits. And this phone app is a very easy and ubiquitous way to sort of assess that. So something we're going to be working on in the future. Okay, so we've shown that humans are very visually dominant. So one question is that, vision is an aspect of perception. How else can we leverage humans' visual acuity? And this leads to the paper that I believe was circulated about the visual perception of stiffness, where we were motivated by this idea that humans can extract latent information from visual observation of motion. So from these point lights on the screen, you can very easily tell that someone was walking, now jumping, and now climbing a set of stairs, just from watching these dots on the screen. Which led us to ask from dots on the screen move, can people perceive limb stiffness from solely visual observation and motion? So what we did was we had people sit in front of a computer screen, they observed this two-link manipulator move exactly like so, and we asked them what rate the stiffness. And what we found was quite remarkable. People were able to positively correlate their stiffness ratings with simulated joint stiffnesses. And I want to highlight that this is really remarkable. Stiffness is a relationship between motion and force, namely displacement and force. But from looking at a simulation, you have no access to force information. So you're solving this equation, F equals kx for k, without F, only x. You can't get force information because you can't interact with the object. And this work is really exciting because it highlights on the fact that we can use motor perception to learn more about motor control. If we ask how were people able to do this task, well, the only working hypothesis that as to how people were able to do this task is the controller that we embedded in our simulations was based off of a lot of literature on how humans produce their own motion. And based on this idea of this action perception relationship, if you have, you can use your motor action controller to perceive something. So the fact that they were able to perceive this says that the controller we embedded has some congruency with their motor action. So sort of their internal motor controller, their motor action controller. And to sort of internalize this relationship, this coupling between motor action, motor perception, we can think about, for example, how babies learn. They come out the womb not knowing how to walk or talk, but from perceiving, observing the people in their lives do these tasks, they are able to build their own internal model of how they can do these tasks. So that's an example of how perception leads to changes in your motor action controller. In the other direction, if you wanted to understand how I'm speaking or understand the words that are coming out of my mouth, but I'm not saying anything, what you can start to do is you'll have an internal model of how you would say certain words, and then from your perception, you'd be able to tease out the words that I'm saying based off of your internal model of how you would say those words. So that's an example of motor action to motor perception. And this ability to use perceptual studies to understand motor control is very powerful because perceptual studies are cheaper and easier to employ. This study, for example, only required a laptop, which most of us have in front of us, and are quite ubiquitous nowadays. Whereas motor control studies often involve a lot of expensive lab equipment like robots and must be conducted. The other key aspect of this work is it suggests a non-contact, visual-only method to measure stiffness, which is often akin to rigidity. In stroke patients, we talk about this idea of having abnormal stiffness or rigidity, which is involuntary co-contraction about a particular joint. And this is an important biomarker and something that physical therapists aim to rehabilitate in their patients. What we've shown is that we can now start to quantify this abnormal stiffness or this rigidity in stroke patients using only kinematic information, which is very exciting because due to key point detection algorithms like OpenPose and MediaPipe, we can get kinematic information during in-home rehabilitation using low-cost cameras. So now we can start to track patient progress during the rehabilitation in-home and outside of the clinic, which is very exciting. Okay, so I had previously shown that people can estimate stiffness using visual observation. The next question becomes, can people estimate damping, which is a relationship between force and velocity, using solely visual observation and motion? And then further, we wanted to also probe at this idea of can we improve their performance via coaching? As we've shown, physical therapists might want to be able to possibly do telemedicine and want to estimate patients' rigidity, or in the damping case, the dual is called spasticity, involuntary resistance to changes in velocity. If we want to build a physician's internal model of being able to perceive these tasks, maybe providing coaching during their training can help. So we wanted to probe at this. And I had an undergrad in the lab, namely Leah Huang, sort of run this study, where it was the same experiments designed as a stiffness study, where we had participants observe 30 simulations, this time of 6 different joint damping values, shown 5 times in a block randomized order, where we asked them to rate the arm damping. And in this experiment, we had 3 different control groups, which I'll go over in a second. And we also had 2 sessions. So session 1, session 2, and in between the sessions were a coaching intervention. And amongst the 3 groups, session 1 was all the same. Basically, they just observed the 30 different simulations and rated the arm stiffness. Now, where groups differed was in this coaching. Namely, the first group received no coaching. They just did the experiment, took a break, and then did the experiment again. However, the second group received a coaching, basically where we told them to observe the endpoint speed when trying to make your estimates. And then the third group, we told them to look at the elbow angle, so the speed or the rate of change in which the elbow is opening and closing. And then again, all three groups, after getting their coaching intervention, they ran the exact same study again. And I don't have enough time to show you the full coaching videos, but here's a snippet of it, where in the endpoint coaching, they're being told to observe the speed of the hand or this endpoint. And then in the elbow coaching video, they're being told to observe the rate of change at which this arm opens and closes. To further probe at this idea of, okay, we're giving them coaching, are they responding to coaching? After each session, we had them fill out these surveys. The first survey wanted to probe at what location were people looking at, and we asked them to report the percentage of time they're looking at a particular location, namely the hand, the elbow, or the elbow angle. So the hand and elbow being in Cartesian space, the angle being in joint space. And then we also had wanted to see what specific motion characteristics were they looking at. So we asked them to report the percentage of time they used displacement, velocity, acceleration, or jerk to make their estimates. And then also to just further scrutinize people's reporting, we incorporated eye tracking using the pupil core eyeglasses. And Talia wrote this very nice script that can determine if you're looking at the endpoint or the elbow or either. So how did people perform? So across both sessions and across both groups, what we see is people's the simulated joint damping and the participants' damping rating. And we see a positive linear effect of simulated joint damping on stiffness rating. So people correctly correlated increased damping with the simulated damping that they observed, which is good. This is a positive result. It shows that people can innately perceive damping visual observation of motion. The next thing I want to highlight is this representative subject data. And what we did was, what's shown here is, again, the simulated joint damping and the subject's rating. And the dots represent each trial, where larger dots represent a repetition of this simulated damping with this subject rating. And basically what we can do is we fit a line, and from that line, again, measure the coefficient of determination. And if subjects did this task perfectly, we would see a fit of a line that was just straight, slope of 1, all the dots on that line, and this coefficient of determination would approach 1. So what's shown here is in block 1, we see the subject's performance, and we see some scatter about this line that does have this positive slope. But as they improve and there's less scatter about this line, they're more confident in the results, their coefficient of determination increases. So we can use this coefficient of determination as a performance metric of how participants perform. So looking at this coefficient of determination, we see different subjects' performance in session 1 and session 2, where the colored lines are the individual subjects of the 3 different coaching groups, and the solid lines are the means across subject, where the shaded region is a standard deviation. And we see all subjects generally increase, but what we wanted to see is compare how did coaching affect. So what we wanted to look at was the change in this performance metric, or the change in R squared from session 1 to session 2. So basically, this is the difference here. And what we find is that elbow coaching led to a significantly better performance than no coaching, whereas endpoint coaching did not. So the key takeaway is that elbow coaching led to significant improvement over no coaching, which tells us that, to do this task, people should be looking at the elbow. And further, we wanted to scrutinize, okay, we've shown that this coaching group actually had better performance, but the question is, were they actually doing what they were coached to do? So we have these survey results basically on the location that they were looking at. And again, we show the change in percentage of what they were looking at from session 1 to session 2 across the different coaching groups for the change in hand percentage, the change in elbow percentage, and the change in elbow angle. And what's important to focus on is our endpoint coaching group here. We should see that they significantly reported more looking at the hand, which is what they did. This is good. And then our elbow coaching group, they significantly reported looking more at the elbow angle, which is what they were coached to do. So these two results highlight that participants were looking where they were coached to look. The next survey result looks at the motion, namely asking what motion characteristics people report looking at: displacement, velocity, acceleration, or jerk. And they were specifically coached to look at velocity. So again, looking at the change in the people's reported percentage across these motion characteristics, what's important is our coaching groups and velocity. If they did what they were told to do, we would see significant performance in velocity over the change in velocity over the no coaching group. And in fact, we do not. In fact, a lot of subjects reported looking less at velocity, even despite being instructed to. So the key result here is that participants did not attend to what they were coached to observe, velocity. So the key takeaway here is that humans can correctly infer changes in limb damping from non-trivial changes in multi-joint limb motion. And this suggests yet another aspect of mechanical impedance is encoded in humans' internal model to do this task. And this has a nice corollary impacts, which suggests that non-contact visual-only technique to assess damping, namely spasticity, can be leveraged in rehabilitation paradigms. And then a new result is that we showed coaching improved people's ability to estimate limb damping. And this is exciting because automated coaching can be leveraged in teaching surgeons and physical therapists to estimate mechanical impedance from visual observation. We've talked a lot about how this can be beneficial for physical therapists. Let's kind of motivate this idea of how it can be beneficial for surgeons. So currently, there is a push for for minimally invasive robotic surgery. And recently, surgical robots do not provide haptic feedback. So basically, a surgical robot is a teleoperated system where a surgeon will sit at what they call the leader console, and they'll control some tools elsewhere that are now interacting and cutting and doing surgery on the patient. And because this is an electrical connection, this electrical connection kind of cuts the inherent haptic feedback that you would get if you were using directly a tool. And prior surgical robots have not incorporated that haptic feedback to surgeons. And this sort of haptic feedback is useful. Surgeons reported that, when they're doing hands-on surgery, something that they may see is looking at tissue dynamics to determine if this tissue is a malignant tumor versus, biological tissue that needs to be inside the body. They may poke at some tissue and say, this tissue feels hard. That means it needs to be resected. It needs to be cut. But during robotic surgery, because you don't get this haptic feedback, this sense of force from your robot, you can't do this sort of task. So surgeons now report they're able to understand tissue dynamics from visual observation, visual perception. However, when you ask how are they doing this, they don't necessarily have a good understanding of how they built this internal model of the visual perception of these tissue dynamics. And if we can, again, pull back the layers of how people are doing this, we can now start to leverage this automated coaching to be able to train surgeons on how to build this internal model and possibly reduce their training time required to do these tasks. So looking at some of the future work of the perception of dynamics, the whole crux of this work falls in the assumption that people are able to perceive this task because the underlying controller that we've created in our simulations is consistent with how they produce this motion. So now we want to sort of stress test this motor action, motor perception relationship by asking people to perceive physical stiffness and physical damping. So I had over the summer 2 RU students working with me to design and build this elbow exoskeleton, which because it has a motor and an encoder, it can now apply external stiffnesses and damping about this joint. So now we can look at perception of stiffness and damping in the physical domain or in the action domain. And because we have this in the action domain and we had this previously in the perception domain, the visual perception domain, we can start to stress test the coupling between these two. And now currently a PhD student, Aaliyah Mazeo in the lab is working on this particular task. And some interesting questions we're looking to ask are, can we use this device to build a better internal model of abnormal stiffness, i.e. rigidity, and damping, i.e. spasticity in clinicians? Basically, if we want clinicians to be able to visually perceive rigidity and spasticity and their stroke patients via telehealth, can we use this device as a training device, maybe have them don it on their own so that they can understand, this is what my patients are feeling. And that can help them better perceive these abnormalities when they're diagnosing patients. And the next interesting question is, can we leverage the upper limb elbow exoskeleton to create what I call a dynamic illusion that affects perception and dynamics? So this is basically the opposite. Can we use maybe one domain, train them in the motor action domain, but train them incorrectly, and then ask, does this affect their perceptual controller as well? And that would really show us that there's this coupling between the two. And then lastly, more out there idea is that stroke patients for us researchers, their time is very valuable, and conducting research with them becomes sometimes a difficulty. So one idea is, can we use healthy participants to understand how people might adapt to rigidity and spasticity, these abnormal co-contractions about the joint? And then when we can use this elbow exoskeleton to simulate this information, or simulate this abnormality in healthy patients, and start to see how they respond, and maybe possibly can collect some aspects of incorrect information, incorrect data, not purely ground truth data about stroke patients, but it's simulated data that might get us a little bit further. So just to conclude, my research kind of sits at this idea of trying to use simple models and control theory to understand human motor control, perception, and learning, to sort of bridge this gap between humans and robots. And I hopefully convince you that this paradigm is valuable today. But just to finish with some closing words, robots continue to fall short of human performance. And I believe closing this gap requires linking motor control, so this forward path, also with motor perception, this feedback path. And I think studying both offers a path to better robots and better rehabilitation. So thank you for taking the time to listen to me today. I guess I'll pause here and ask if you have any questions.
Awesome. Thank you so much, Dr.
Thank you.
Yeah, thank you so much. There are a couple of questions on the chat. I can go ahead and read. Okay, so Tristan is asking, how does one account for the noise using this method?
Tristan, which method are you referring to?
My bad. I had sent that out when you were talking about the linearization versus the exponential, and using like a 3-point curve to then kind of determine. But then like my question was like, if you have a sensor that could be faulty and you're using like a 3-point linear adjustment, how do you account for like noise when you see that? Or if you got like bad sensor reading, could that like throw it off?
Yeah, so with much less data points. So you're talking about in the cross-modal matching when there's in the cross-modal matching when we're doing the reduced optimized method, we have
Yes.
less data points. So yeah, the less data points are more susceptible to noise. But in the paradigm, I guess I can go back. In the paradigm, basically the optimization not only tells you tells you how many points, but it tells you which points. And basically across all of our subjects in our data set, we found these specific points. I believe it was like 2 nines, 4 nines, and yeah, here we are. It was 2 nines, 4 nines, and 8 nines. These points are actually the least noisy. They provide the most amount of information, which is why they were used in this linear fit.
Oh, okay. That makes a lot more sense. Thank you for the clarification.
Thank you for the question.
Okay, so Edward is asking, I would be concerned about the refresh rate of both sensory inputs. Could confound the results. Maybe Edward.
Yeah. Sorry, I was talking about the when you're doing the haptic and visual what's it called, feedback. Let me see. I think it was when you're comparing haptic and visual feedback and finding that visual feedback that had greater accuracy. And I was just concerned because they're looking at a screen and holding like a virtual ball. I'd be wondering like what the refresh rate to the haptic feedback is, because if there's any delay in that might make somebody like they would like be overcompensating and kind of like not reacting to it and at the same speed.
Yeah, that's actually a really good point. That's a really good point. I hadn't thought about that. And actually, I mean, ultimately, the idea of the cross-modal matching is to sort of bring these two together. But the cross-modal matching is actually done in a paradigm where you're not doing a particular task. So it wouldn't even account for sort of that feedback delay in the visual,
Yeah.
the sensory loop. So
Yeah,
yeah,
because
that's
yeah,
actually
I'd
a
be
really good
worried
point.
about the calibration test because it didn't calibrate the reaction speed to each sensory input either. So maybe that's something that could add to it.
Yeah, that's a good point. Yeah, that's definitely something we could probably test for in a different experiment. Yeah, thanks for the question.
Bro. Yeah, pretty interesting. Thank you.
I see Riley asked, to what extent could visual dominance have been the result of media experience with your subjects, perhaps training them better with visual inputs? Could perhaps sound have been better comparison when working with computers? Audio feedback is more common than haptic. So I think you're kind of getting that maybe people had prior experience with just doing visual tasks. That's why they perform better. And I think generally, yeah, I think just in general as humans, that's kind of our default modality of trying to sense the world is vision. Um, so I think yeah, just inherently everybody is pretty visually dominant.
Yeah, I guess what I was getting at is more at the context in which you're doing the testing is working very much with a computer, right?
Mm-hmm.
And it's almost like a game in a sense where you're trying to, hold that ball. But if you play games, uh, there's more common a audio stimulus and video stimulus than there is a haptic stimulus. So it may
Mm-hmm.
be people who just had played games or just watching shows or whatever. The use of visual and audio is very, very common when interacting with a screen, whereas the use of
Mm-hmm.
haptic feedback isn't. So maybe
Mm-hmm.
humans are just trained better in that context to react to visual than they are to haptic, and perhaps if the use of sound could kind of get into the fact that we are also kind of trained with sound. Like you watch a horror movie, they make it scary with sound, so we react to that stimulus. We don't really,
Mm-hmm.
there's not as much media that uses haptic to kind of influence how we are behaving or acting. And we have contextualized this test with a screen and an interaction.
Yeah. Yeah, that's a good point. That's yeah, we kind of did think like again the visual dominance. I mean, yeah, you hit on another point about this visual dominance is that probably visually dominant in playing these sort of games. It really is a game. That's the whole motivation behind the rehabilitation aspect. Is it is supposed to feel like a game, which is why in the future work we do want to push towards just doing two haptic domains, just more so stress test this concept of perceptual equity. But yeah, that's a good point. Thank you, Riley.
Thank you. Also, a great presentation. Good job setting up the problem and the gap to contextualize what was coming. That's a very good technique, and appreciate it in your presentation.
Thank you.
Yes. Can I ask my question? Can you hear me?
Yes.
Yes. Yes. To jump back on what Riley was saying, at the beginning you showed a very interesting graph of the gap, right? What is your feeling? Like as you said, we're doing more with less, and in my mind, I would think that this is just the speed at which I don't know we handle we handle information and instinctively process it to to bring all of this together. So what's like uh, how can we quantify what's missing to robots for them to put all of this together on this
Yeah.
task?
So very, very difficult question. And that's kind of what the field is trying to answer. And I'll give my take. which may be different from someone else's. But
Mhm.
yeah, I think basically you're talking about the motivation behind basically humans, their hardware sucks compared to robots,
Yes.
right?
Yes.
We're better at tasks, right?
Yeah.
So
Yeah.
the question becomes, what are humans doing? And that's kind
Mhm.
of why I look at this approach with simple models. I really believe that because robots have such better computation than humans, there's
Mhm.
no way we are doing the computations that we require robots to do.
Mhm.
I give a good example is opening a door, right? To open a door,
Mhm.
you should be applying a normal force to that door, and
Mhm.
due to the curvature, the radius of curvature of the door, that normal force is always changing instantaneously. You and I, when we
Mhm.
open doors, we don't think about the radius of curvature of door. We do something that
Mhm.
approximately works. And I think kind of peeling back, in fact, we grab the door and compliantly pull it, and that compliance allows us to basically the vector of our force applied doesn't necessarily matter too much.
Mhm.
But I think peeling back and trying to understand what are these simplifying control techniques that humans are using and implementing those into robots is kind of where bridging that gap can.
They're having. All right. All right. Something else on your um, is it not a limited sample set of 12 participants for that first paper? I know there's like there's like a lot of blocks and information, and so we're just looking at the data and not just really which participants it came from. And isn't it tied to this the fact that you can fit a linear model on this?
Are you asking if the participant population may have biased the results?
Yes, basically there's so little. I don't know. And I'm very not knowledgeable about this, but
Yeah, so in human subject studies, it's always kind of the question of
Mhm.
is your population rich enough? Ultimately, you're
Mhm.
doing this research on a college campus, so everyone ends up being an 18 to 22-year-old college student.
Mhm.
So our all of my studies are almost always kind of biased to that population. Um,
Mhm.
but as far as this N of 12, yeah, there was a small start. But once we got to the sense match paper, we actually basically replicated this study and
Mhm.
got the same result. So, as you kind of build
Mhm.
on your, I think this may have had another 12 participants. So as you start to build out and do more and more studies, that participant population becomes greater. Uh, and,
Okay.
the one thing you always worry about in human subject studies is outliers and like trying to understand your outliers. In our particular case, we didn't have any. So I think it was
Mhm.
decently representative.
Okay. And something else I did not understand is we're trying to calibrate the machine to make sure that it's not being biased in the experiments. That's something I did not really understand.
Yeah, that's a good. It's kind of hard to completely understand. Um, it's yeah, you didn't. It's not simple to explain.
Mhm.
So the key idea is basically that um, we have two modalities, two sensory inputs, right?
Mhm.
And we want them to be equally useful. And the
Yeah.
idea is that if they're equally useful, then people should be able to use them equally. So that's the whole idea of cross-modal matching. And we try
Because
and tease this.
we're trying to bring back these sensory feedback to those patients, right? It's gonna
Mhm,
change over time. They're gonna improve maybe, so
mhm.
once you calibrate, like you stay at the same status. Like this is what I'm trying to.
So the calibration is a pre-step to the experiment.
Okay.
So it's not the experiment. The experiment may have some sort of, it may be very different from what we had, or it may be the
Oh.
exact task. The pinch task might be an experiment. But the idea is that you want to create a task such that they're using multiple sensory inputs to
Mhm.
try and perform the task. And to
Oh.
encourage them using
Okay.
multiple sensory inputs, you want to equate them.
Okay. 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 Perfect. Thank you.
Thank you.
I had one more question about the computer. I was kind of wondering about the predicting the visual perception of arm damping. I was kind of wondering if you knew anything about like how good like computer vision algorithms are at predicting damping or stiffness and how they perform compared to like the human estimation that you found.
Yeah, that's a good question. It's something I've been meaning to look into. I haven't just yet. Um, I could imagine that with enough data, um,
Mhm.
it could, I feel like it should be easier for a computer to do. And in fact, I
Mhm.
think one time a long time ago, I just did a simple kind of not even a neural network, but just like a regression on a large amount of data for this. And it performed pretty well, just because
Mhm.
that's what computers are doing, pattern recognition.
Yeah.
And again, that's what humans are doing. But one thing that is kind of exciting about this work is that um, if we can basically tease out and have a good understanding of the relationship between if we have a good understanding of the motor controller, the baseline biological motor controller, then
Mhm.
we can start to use these simulations to train the data, right? So
Mhm.
now we can sit here and create infinite amounts of trainable data because we can just simulate the trainable data as opposed to getting data from, um, stroke participants or healthy populations or just different large amounts of populations.
Mhm. Mhm. Awesome.
Hey, yeah, sorry, just wanted to, I don't know if this makes sense, this question makes sense, but I think I mean I enjoyed the presentation, and particularly this slide that you're in. I'm wondering whether the research that you're doing in particular, I think you reached a point where you had a hypothesis and you weren't able to your evidence, your data wasn't able to support it. And I'm just wondering if that um, some of the work that you've been doing can be used to better understand the whole the learning models that we have as humans. So I don't know if you went into this. I was trying to follow as much as I could, but it seems as if you sort of reached a point where you could understand, you could see that um, that that humans have the ability to learn a little differently from the sensory inputs in a way where they're sort of modifying on the models that they have um, on the fly versus the machines and so forth that the would. So I don't know if this is the right question and so forth, but I'm trying to tie the two of these together in my own mind and just wondering if you have any insights from the work that you're doing um, on that and related to like how humans themselves learn to adapt and so forth. Like you mentioned this thing about like babies learning and so forth.
Yeah, so I think one aspect of research that I'm trying to get at is trying to understand skill acquisition. Um, and I think skill acquisition in terms of humans is very different than skill acquisition in terms of robots. I think um, possibly that example I sort of gave of opening a door. I think we learn how to do things and don't necessarily think about the mathematical models required to do them, which are necessary when you're trying to get a robot to do something. It has to have some sort of mathematical representation. So, like I said, I think one previous aspect, I'm really interested in skill acquisition. I am, I think one thing that I haven't had the chance to break into yet, but I'm planning to soon, is actually trying to learn about surgical skill, learn how humans learn surgical tasks to try and again automate this idea of automated training to improve surgical training. Um, and as far as like the part of your question about comparing and contrasting how humans learn and how robots learn, I'm of the opinion that like machine learning is great, but sometimes it can be a bit of a black box. And for robots, it's not necessarily in some cases how they learn, but that they do learn. And you know, that's great for a robot that you can just quickly replicate. But for a human, it's important to understand how they learn because that's how you teach them. You can't teach someone if you don't understand how they learn.
Yeah, sorry, it's just like super early for me, so maybe I'd like ask the question. You answered it right. And I think what I'm saying there is, if you were to switch some of the sensory inputs on and off, and the humans were still able to learn, and so forth. I guess I'm moving in that direction. Is like whether you think that would help you learn more about how human beings are learning. Like you know, the visual field is very dominant, and there's some other sensory inputs that humans are having that's very dominant. But I'm just wondering if you thought that some sort of approach like that would work, sort of just get a better understanding of, because I assume there's some sort of inherent learning, like meta learning modules that we have, where as the sensory inputs coming in, we're trying to figure out how to, acquire a certain skill or to accomplish a certain goal and so forth. But as you said, like everybody's, the calibration is necessary because different people use the sensory inputs in different ways. I guess is how I'm trying to say it. And then, so is there a way of tuning or recalibrating and so forth, and learning how one person adjusts their models from one form to create a new model, and to see how that transition, or yeah, if that could help in any way. Sorry if I sound very disorganized in my.
If I understand correctly, you're kind of talking about research paradigms where you're trying to see more so how do people adapt when you turn off different sensory inputs. And I think, yeah, definitely that's very useful. And a lot of people do that. I haven't necessarily dipped my foot into that sort of specific learning paradigm just yet, but there's a whole field of like a lot of computational motor learning people who will look at very stringent learning paradigms and see how people adapt and learn particular tasks.
Thank you, Dr. West, for a wonderful presentation. I hope everyone enjoyed this, like a lot of things we got from today's presentation. Yeah, good luck with your postdoc. See you at Georgia Tech.
Thank you so much, Dr. West.
Thank you for having me.
Thank you. Thank you, everyone. Have a good weekend. See you all in next week.
You too.
Thank you. Bye-bye.
Yeah.